Hello everyone, welcome to this lesson. In this lesson, we're going to be looking at the test of independence. This is a hypothesis test used to determine if two variables are independent or dependent. And these variables are going to be qualitative variables. In other words, these variables are going to be categorical variables. This is the second hypothesis test that you see for qualitative variables. You're going to notice that the test of independence and the goodness of fit test are really similar. I will make sure to highlight the differences. Let's start by reading the learning objectives. By the end of this lesson, you should be able to state the null hypothesis and the alternate hypothesis for the test of independence. You should also be able to organize the observed and expected count for each category using a table. At the end of this lesson, you should also be able to calculate the chi-square test statistic for the test of independence. And you should be able to conduct the whole hypothesis test for a test of independence using the p-value approach. For this test, once we have the observed values and the expected values, we're going to find the test statistic using chi-square equal to the sum of O minus E squared divided by E. This is a formula that we use for the goodness of fit test. So let me give you a quick introduction to the test of independence. First, let's talk about when we're going to be using the test of independence. We're going to be using the test of independence to decide whether two variables are independent or dependent. Now, let me be more specific here. I should be writing that we're looking at qualitative variables. So I'm going to make sure to add that on your activity. Again, we're using the test of independence to decide whether two qualitative variables, categorical variables, are independent or dependent. Now, whenever we say that two variables are independent, we're saying that they don't affect each other. So here you can write a reminder that independent means the variables do not affect each other. Now, dependent is the opposite. The variables do affect each other. Now, with this type of test, you're going to have two variables, like I mentioned, two qualitative variables. Each variable is going to have categories. The categories for one variable are going to be separated with columns, and the categories of the other variable are going to be separated by rows. We're going to organize this information using a contingency table. And so the contingency table is going to have the observed values coming from the sample. Okay. Now let's talk about the null hypothesis and the alternate hypothesis for the test of independence. For the null hypothesis, you're always going to say that one variable is independent from the other variable. So in general, we say variable 1 is independent from variable 2. And think about it. Here we're saying one variable doesn't affect the other variable. Now, for the alternative hypothesis, we're going to say the opposite. We're going to say variable 1 is dependent from variable 2. I mean, a common question that I get is, can I say that variable 1 is not independent from variable 2? And the answer is yes. You could write not independent instead of dependent. Okay. Now, as always, we have conditions on when we can run a hypothesis test. For this test, we have the same conditions as the conditions we had for the goodness of fit test. We need to make sure to randomly select the sample, and we need to make sure that the expected values for each category or for each cell on your contingency table is at least 5. So 5 or bigger than 5. We're going to be using the same formula for the test statistic. We're going to use the sum of O minus E squared divided by E. And remember, just like what we did with the goodness of fit test, we're going to need to find O minus E squared divided by E for each cell on the contingency table. And then our next step is going to be to add all those values, right? Here it says, take the sum of all those values. Okay, so I'm just going to write then add all those values. Or I'm going to write then add all the O minus E squared divided by E values. Now, recall that when we're looking at this formula, O stands for the observed value of a category. So O are the observed values, the values that you have coming from the sample. Now the E stands for the expected value. And we have a expected value for each of the cells on the contingency table. To find the expected values, we're going to use the probability rules that we had for variables that are independent. I will go into details about this. We do have a formula for the expected value, and I will be explaining how that expected value formula came to be. Now, the degrees of freedom for this test are going to be calculated as follows. DF, degrees of freedom, is equal to the number of categories for variable number 1 minus 1 times the number of categories for variable number 2 minus 1. On the contingency table, we're going to be able to see how many categories we have for each variable. So for example, if you have 5 categories for the first variable, then your degrees of freedom is going to be 5 minus 1 times, now let's say that the second variable only has 4 categories. So then here we would be multiplying by 4 minus 1. We're going to make sure to take a note of the number of categories we have for each of the variables. So again, this was just a quick example to see how we calculate the degrees of freedom. Okay? Now, once you have your test statistic and the degrees of freedom, then you're ready to find your p-value. For the p-value, we're wanting to find the area on the right tail of the chi-square distribution. Our lower bound is always going to be the test statistic, and your upper bound is going to be a really large number, 1E99. So notice, on the calculator, we're using the chi-square CDF distribution. We're going to enter the lower bound, which is the test statistic, comma, the upper bound, which is a really large number, 1E99, comma, degrees of freedom. On Google Sheets and Excel, we're going to be using the function equal CHISQ, which stands for chi-square, .dist, which stands for distribution, .rt, RT stands for the right tail, and then we're going to open a parenthesis, we're going to enter the test statistic, and then we're going to enter the degrees of freedom. Here, this function on Google Sheets and Excel is going to give you the area to the right of the test statistic, which is the area that you're trying to. Once we have the p-value, we can compare the p-value with our alpha value and make a decision of whether we're going to be rejecting or failing to reject the null hypothesis. And then finally, we're going to go ahead and write a conclusion for the test. And so now let me go into details about how we're going to be calculating the expected values. Like I mentioned before, we're going to need to find the expected value for each of the cells on the contingency table. The way we're finding this expected value is by assuming that the null hypothesis is true. Okay, remember, that is the rule for every hypothesis test. When you conduct a hypothesis test, you need to assume that the null hypothesis is true until you provide sufficient evidence coming from a sample, okay, to reject the null hypothesis. And then sometimes we come back and we say we don't have sufficient evidence to reject the null hypothesis. Okay? So the idea here is that we're assuming that the null hypothesis is true. We're assuming that both of the variables are independent. With that in mind, we can come up with the formula for the expected value. The expected value formula is as follows. You're going to take the row total times the column total, and then you're going to divide by the total number of individuals in your sample. Okay? Now, before I go into details about how we found this formula, let me show you how you would use it. Okay? So I'm going to fast forward to the example we have here below. Here on this contingency table, you have the observed values. So let's look at one of the cells. Here, we're seeing that from this sample, 111 individuals are students from a community college. And those 111 individuals do about 1 to 3 hours of volunteering per week. So this is what we're observing. Now, if the variables were independent, how many would we expect to see in that cell? Okay. So we're going to go ahead and use the formula that we have above. The formula says to find E, take the row total. Okay. So for this row, we have a total of 255. Then the formula says now multiply by the column total. For this cell, we're looking at the first column. The total for that column is 298. And then the formula says now divide by the total number of individuals. So we're dividing by the total number of individuals. Remember, the total number of individuals from the sample is found on the lower right corner of your contingency table. So here, the total number of individuals in this sample is 839. And so this here, if you go ahead and enter this on your calculator, this is going to give you the expected value for the first cell. Okay? So again, that is how we're using the expected value formula. Now, I do want to go into details about why the expected value is calculated using this formula. So here, we're going to talk about the formula. And so again, when we're conducting a test of independence, we're going to assume that the null hypothesis is true. In other words, we are assuming that the variables are independent. Now, if we know that two events are independent, okay, so let's say if A and B are independent, then we know that the probability of A and B happening is equal to the probability of A times the probability of B. The multiplication rule, P of A and B equal to P of A times B, is going to help us find this formula that we have for the expected value. Because think about it. If we're looking at a contingency table and we want to know the probability of A, so for example, if we want to know the probability of someone in our sample volunteering 1 to 3 hours, if we want to know that probability, we're going to say, well, take the number of people who volunteer for 1 to 3 hours. We have a total of 298 and divided by the total number of people in your sample. Here we're looking at the column total and the total number of individuals. Okay, so the probability of event A would be the column total divided by the total number of individuals. Now, the probability of B, let's go back to the contingency table. Let's say we wanted the probability of someone from our sample being a community college student. In this case, we would say, well, how many people in your sample attend a community college? We would say, well, we have a total of 255. So notice, we're looking at the row total. So again, 255 divided by the total number of people that we have in our sample, divided by 839. Okay? So we're simply saying take the row total and divide it by the total number of individuals. That is how we would calculate the probability of A times the probability of B using a contingency table. Now, let me make a replacement here. Instead of writing the total number of people, that's a long sentence there, I can go ahead and write N, right? N is the total number of people in our sample size. So that looks a little bit nicer. So this would be the probability of A and B. Now, when we're finding the expected value, we want the number of individuals. The probability that we have here above, the probability of A and B, can help us find the number of people or the number of individuals in that specific cell. So to find the expected count, we need to take the sample size, the number of individuals in our sample, and we need to multiply by the probability of A and B. So we're multiplying it by this expression here. So notice here, we are multiplying by N. We can cancel that multiplication with one of the N values that we have on the denominator. Why? Because N divided by N is just 1. And so once we cancel N, we are left with the column total times the row total on the numerator. On the denominator, we're left with N. And that is how we've ended up with the formula that we have here above. Okay? If you're wanting to find the expected value for any of the cells on your contingency table, you're going to take the row total times the column total divided by the sample size, which is the total number of individuals. Here, I went through all the thinking process that happens to come up with this formula because, as I mentioned before, the expected value is computed using theory, using rules of probability. I wanted to show you that indeed we use the multiplication rule for probabilities to come up with the formula for the expected value.